Thank you very much, Rolando. And thank you to Dima and the organizers for the chance to speak. I've really enjoyed this conference so far. I can't remember the last time I learned so much in 2 days. Maybe it was back when I was a PhD student sometime. But it's been great so far. So anyway, enough yammering. I'm going to be talking about Horn's problem and free probability. OK, so Horn's problem, and this is joint work with Colin, who's based in Taiwan, Octavio, who's here, that gentleman there, and Joscha, who's based in Germany. And individual joint works with each of these three. So Horn's problem is concerned with the way eigenvalues of deterministic matrices behave when we add them together. So consider the following really simple problem. Let's say I have two Hermitian matrices, A and B, and I know their eigenvalues. Whoops, that's backwards. Okay. What can I say about the possible eigenvalues of the sum of these two matrices? In other words, given these real numbers AI and BI, what are the possible real numbers CI that can occur as the eigenvalues of A plus B? Well, if you think about this, it has to be the case immediately that these CI have to satisfy a trace equality. And it's a basic linear algebra exercise you can do to check that the largest of the CIs is controlled by the largest AI and the largest BI. And likewise, you can say something similar about the smallest of the CIs. There are a bunch of other inequalities that these CIs have to satisfy involving the coordinates of the AIs and the BIs. For example, Wales showed in 1912 that this inequality is satisfied. Over the 20th century, mathematicians developed more and more inequalities that these CIs have to satisfy. But it wasn't until the 1962 work of Horn that this was really tackled systematically. So Horn used this kind of intricate recursive procedure to define a collection of triples ijk of subsets of the integers 1 through n. And Horn conjectured that if you associate with each of these triples of subsets an inequality, then these inequalities, this collection of inequalities, would fully classify the possible eigenvalues of the sum of two matrices. Namely, Horn conjectured this result, which was proven in a culmination of works in the 90s by Klatschko and finally Knudsen and Tau. Namely, that a bunch of real numbers AI, BI, and CI are the eigenvalues of Hermitian matrices satisfying A plus B equals C, if and only if their traces match up and all of these inequalities are satisfied. So this is these inequalities are a necessary and sufficient condition for these CIs to be eigenvalues of AIs and BI, for these CIs to be the eigenvalues of some Hermitian matrices A plus B. Okay, so you could also note that if you subtract this inequality from this trace equality, you get a corresponding inequality with the inequality sign going the other way and the complements of these sets. So that gives you a way of making the problem maybe a bit more symmetric in your head. Anyway, these sets, these collections Tn of subsets are quite complicated. But the kind of short story here is that the possible eigenvalues Ci of the sum of two matrices are, well, the Ci are possible eigenvalues of the sum of two matrices if and only if they satisfy a bunch of inequalities involving the AIs and BIs. Okay, now what I want to do is think about how a free probabilist might approach this problem or study a variant of this problem. So namely, let's consider a free probabilist version of this problem. Let A and B be independent, uniform, random Hermitian matrices. These are large random matrices with eigenvalues approximating some measure mu and some measure nu. The free probabilist's version of the Horn problem would be, what can we say about the probable or typical behavior of the spectrum of this matrix, A plus B, as n tends to infinity? And of course, the free probabilist's answer to this problem is that the eigenvalues will likely approximate the free convolution. So if we take a typical matrix A, where I'm using typical in a kind of informal sense, if we take a typical large matrix A with eigenvalues approximating this guy, and a typical large matrix B with eigenvalues approximating this guy, and we add them together, their eigenvalues will likely approximate this guy. Okay, but can we relate the two perspectives? So we have this deterministic perspective describing the possible eigenvalues for fixed n of a sum of two matrices. And we have this free probability perspective describing the probable eigenvalues that occur as a sum of matrices for large n. So this kind of motivates the rest of the talk. In section 1, we're going to look at free convolution as a solution to the Horn inequalities, but understood asymptotically. And in section 2, we're going to look at free convolution as a solution to an optimal transport problem. And in section 3, I'm going to touch on themes from Harry's talk about how free convolution appears as the solution to a minimization problem. If you look carefully, I've used the here and the here and the here. That's because in the first part of the talk, free convolution is going to be one of many possible solutions to the kind of asymptotic Horn inequalities, whereas in these latter two sections, it's going to be a sort of unique solution to certain problems. Okay, so these asymptotic Horn inequalities, or limiting Horn inequalities. Well, combining perspectives on the Horn's problem solved through Horn inequalities and the free probability version of Horn's problem kind of suggests that if you take two bunches of real numbers, AI approximating some measure pi1 and BI approximating some measure pi2, then if you define, loosely speaking, a collection of reals, CI, in such a way that they approximate this free convolution, then it should be that in some informal sense, they're a canonical solution to the Horn inequalities for AI and BI. And so the kind of idea of this section is we want to find all probability measures pi3 that can occur as kind of limiting solutions to the Horn inequalities for AI and BI, approximating certain measures pi1 and pi2. Okay, this is a bit imprecise. So let's make this a bit more precise. So what we're doing here is we're kind of interpolating between these two perspectives. So we have this deterministic perspective describing the possible eigenvalues for fixed n, and the free probability perspective describing the typical values for large n. Whoops. And what we want to do here is kind of interpolate between these two perspectives and describe the possible eigenvalues for large n. Okay, so a more precise formulation of this problem is what we call asymptotic Horn triples. So a triple pi1, pi2, pi3 of probability measures are what we call an asymptotic Horn triple if they occur as limits of empirical spectra of matrices A, B, and A plus B. And when I say this limit, this is taken in Wasserstein distance, which is weak convergence plus some stuff involving moments, which rules out any funny business happening.
You're not assuming compact support.
Sorry?
You're not assuming compact support.
No, I'm not, but I am assuming that pi1, pi2, pi3 have finite expectation, yeah. But it can be, if you assume finite compact support, you can get rid of this here. Yeah, exactly, yeah. So the kind of asymptotic analog of Horn's problem is what can we say about this collection H of triples of probability measures? And there's been related work on this idea of characterizing the set H from a kind of operator algebras perspective by the likes of Berkovici, Collins, Dykema, Lee, Friedland, Fulton, many more. But we'll be interested in characterizing this set H from the perspective of the Horn inequalities themselves. In other words, how do these inequalities behave asymptotically? So just recapping, that's our set H. It's the set of triples of this form. Let's observe immediately that any collection of triples of this form of probability measures must satisfy this condition on their first moments. This is a kind of asymptotic residue of the trace equality. However, to describe the kind of other, it turns out that these pi1, pi2, pi3 satisfy a bunch of inequalities that are asymptotic analogs of the Horn inequalities. But in order to describe these, we need to actually kind of unpack pi1, pi2, pi3 in terms of their quantile functions. So these other requirements for pi1, pi2, pi3 to be a Horn triple are given in terms of the quantile functions, where qi is the inverse of the distribution function of pi I. So there's an idea of what we're driving at here. Let's take an example of one of the Horn inequalities. So Wieland found this inequality, I believe before Horn's work, relating the eigenvalues of Ci with those of Ai and Bi. Namely, pick any subset, capital I, of the numbers 1 through n. Then if you look at the sum of the Ci's over this subset, it's at least as large as the sum of the Ai's over this subset, plus the smallest r of the Bj's. Okay, let's consider developing an asymptotic analog of this inequality as n tends to infinity. So one way you might do this is So imagine we have n tending to infinity, and we have this giant line of numbers from 1 to n, and we have this subset of this line. If we want to kind of describe such a subset asymptotically, we might describe its local density, f of t, of the number of elements near a point Tn. And with this kind of vague idea, we can develop a kind of asymptotic analog of Wheeland's inequality for these quantile functions. Namely, this third quantile function integrated against ft is at least as large as the first integrated against ft, plus the smallest q of the second. So what we're interested in doing here is somehow characterizing all of these asymptotic analogs of these Horn inequalities. And it turns out that our main result here is a kind of weirdly self-referential result, that the kind of set H turns out to somehow characterize itself. So namely, it's a bit of a strange statement. There's a lot of stuff that's going to suddenly appear here. But so a triple of probability measures, pi1, pi2, pi3, lie in H, i.e. they occur as limiting empirical spectra of sums of matrices. Is that the laser? Yeah. If and only if their quantile functions satisfy this trace equality, and they satisfy a bunch of inequalities involving their quantile functions. This is quite a complicated statement that I'm kind of racing through, but these other inequalities involve all of the other small elements of H. So roughly speaking, each element of H consisting of a triple of probability measures that have relatively small supports within the unit interval. Each triple, we call them Q squiggle, in H that have relatively small support you can add a kind of multiple of a linear function to each quantile function in this triple, and it defines a collection of, defines an inequality that all of the other elements of H have to satisfy. It's not the most transparent statement in the world, but the idea is that somehow all of the inequalities that an element of H has to satisfy are somehow parameterized by the elements of H themselves. So in a certain sense, this set H characterizes itself.
So how does this compare with the Berkovich-Dykema-Lee characterization?
Yeah, I think I'm not sure exactly, yeah. I was about to fumble around.
Can we interpret this as these Horn inequalities?
Yeah, so it turns out that the Horn inequalities are themselves special cases of this. Yeah, I'm actually going to touch on this in a slide in a moment.
Are you claiming that these conditions uniquely specify a set H?
We're not sure about that yet.
Okay.
Yeah. So this gives us a means of interpreting this asymptotic Horn inequality for the free convolution.
So these inequalities on the previous slide.
Yeah.
Can you really check them? Like if I give you, like, P1, P2, P3, will you be able to check whether that's true or not?
Yeah, it's a bit strange because there are various examples of things we know that are in H, and we can plug them in either as the Q's or the Q squiggles, and we obtain some sort of inequality. But it's not particularly transparent or obvious to us why these inequalities hold.
No, my question is, how in practice, would you check this that it is true, right? You have I give you P1, P2, P3.
Yeah.
Ask you to check, okay, are they in H or not, right?
Yeah, I mean, that's the problem with the theorem. It's kind of like a self-referential. Yeah, yeah. I agree. Yeah. So, but yeah, this gives us one way of interpreting these asymptotic solutions to the Horn inequalities. Namely, if Q1 and Q2 are quantile functions of pi1 and pi2, then the quantile function of the free convolution is somehow a canonical solution to all of these asymptotic Horn inequalities. And just finally, responding to what Octavio said, you can actually embed the finite n Horn inequalities back into this set H. And these finite n Horn inequalities correspond to triples of quantile functions that look like this. So for example, these are a triple of quantile functions associated with this triple of sets which define a Horn inequality. Okay, so I went through that quite quickly, but the triple pi1, pi2, and free convolution belongs to the asymptotic Horn system. And the remainder of the talk is dedicated to answering why this free convolution is somehow the natural choice of third coordinate. And in section 2, we'll tackle this via entropic optimal transport. and in section 3 via the statistical physics of hives. So our idea here on free convolution via entropic optimal transport comes from a formula of Marcus, Spielmann, and Srivastava. So consider two diagonal matrices A and B, and consider adding A and B together, but here with a unitary group conjugation, and here with a symmetric group conjugation. Okay, clearly these are different random matrices. This guy on the right is always a diagonal matrix, for instance. They're different random matrices, and they have different characteristic polynomials with different laws. However, there's this remarkable fact that if you look at the average of these two, of the characteristic polynomials of these two different random matrices at any point, for some reason, these characteristic polynomials have the same expectation. Namely, if you take any complex number z and you evaluate the expectation of the random characteristic polynomial at this point z, it's the same with the unitary group conjugation and the symmetric group conjugation. It's a remarkable formula, in my opinion, that seems like it has no right to be true. It's got that kind of freshman stream feel to it, where someone just wrote down something they wanted to be true, and it's amazing that it is actually true. And there's been related work on this by Gorin and Marcus in the context of crystallization of random matrix orbits. And in the finite free probability community, there's loads of work on formulas like this and other remarkable relations involving, for example, products of matrices, minors of matrices, etc. Okay, so our idea here is really simple. Let's let z be a large real number, chosen in such a way that z is larger than all of the possible eigenvalues of a plus b under either conjugation. Our idea is we want to study how this formula behaves as n tends to infinity, where the empirical spectra of our diagonal matrices A and B, or equivalently, they're just their diagonal values, are approximating probability measures mu and nu. We know these two objects have to be the same, and thus they have to be the same as we send n to infinity. So what happens when we study both sides of this equation as n tends to infinity? So let's discuss the unitary group side and the symmetric group side separately. So if, consider this expression here. So we have two diagonal matrices A and B whose entries are converging to probability measures mu and nu in terms of empirical coordinates. How does this quantity behave asymptotically as n tends to infinity? So you can write a determinant as a product over eigenvalues. And unpacking this product, you can write this as an integral of e to the n times an integral of log z minus x against the empirical spectral measure of a plus u minus 1bu. So we know, thanks to free probability, that this measure here converges to the free convolution of mu and nu as n tends to infinity. And it turns out that you might naively guess that then this entire expectation behaves like e to the n times the integral of this against free convolution. And it turns out that that fact is indeed true. You can kind of swap limits and everything you would expect to happen happens. And the fact that this kind of limit, the naive thing you want to happen happens, is due to the fact that this this random measure is very strongly concentrated around free convolution as n tends to infinity. It was actually in one of Harry's slides just a moment ago that this thing satisfies a large deviation principle with speed n squared. So it's just too costly for this random measure to deviate from its typical value and hunt for a more profitable value that would make this expectation larger. So it just concentrates around its typical behavior. Okay, so kind of nothing particularly interesting happened here. Everything that we kind of expected would happen happened. However, if you kind of carry out the same story with the symmetric group side rather than the unitary group side, it turns out that things are a lot more delicate. So,
are you assuming here that z has a positive imaginary part?
Oh no, z is a real number here.
A real number.
Yeah.
So can you get a problem here at the singularity?
No, so z is always chosen so that it's larger than any possible eigenvalue. Yeah, exactly, yeah. So these are, all of these determinants will be positive real numbers for the rest of time. Yeah. Okay, so if you look at the asymptotics of this symmetric group side, it's actually far more complicated. So if you consider the asymptotics of this determinant, if you look at this random matrix here, typically the eigenvalues of this random matrix, A plus this symmetric group conjugation of B, typically they concentrate around the classical convolution of the measures mu and nu. That's what typically happens. However, it turns out that this expectation here gets its overwhelming contribution from unusual events where unusual permutation matrices pair up the eigenvalues of A and the eigenvalues of B, or equivalently, pair up the diagonal entries of A with the diagonal entries of B in such a way that makes this determinant larger than its typical value. So you might imagine that a permutation matrix is a giant square of ones and zeros, and if you take a permutation matrix uniformly at random, the ones of the permutation matrix will be more or less uniformly distributed across the entire square. However, this expectation gets its leading order contribution from rare events where our permutation matrix has its ones appearing in kind of non-uniform positions in the square. And there are results by Wu, Trasaras, and most explicitly by Kenyon, Crow, Radin, and Winkler, describing the kind of deviations of a large random permutation matrix away from its typical values. Namely, the probability that the ones are distributed according to a certain density profile f on the unit square behaves like e to the minus n times a logarithmic energy thingy in f. So you can just do a quick reality check that when f is equal to 1, this integral here is 0, which expresses the fact that usually your permutation matrix has its ones uniformly distributed. Whereas if f is any other density function, or I should say any other permuton, this quantity will be greater than 0. So there's interplay between maximizing the value of this random variable and also maximizing the probability that your permutation matrix is close to f. And what we find is that this interplay is expressed in terms of an optimal transport problem, where this expectation over the symmetric group approximately behaves like e to the n times the solution to an optimal transport problem, where we're trying to find a coupling pi that of two random variables x and y with marginal laws mu and u that makes this expectation of log of z minus x minus y large, whilst also not being too far away, whilst also not being too far away from product measure. So this term h here is called the relative entropy, and it's a penalty for our coupling pi to be far away from product measure. Now, log is a concave function, and that means that the optimal coupling likes to match up small values of x with large values of y, and vice versa, in order to make this expectation larger. Okay, so just to recap, we've seen that we have this remarkable formula relating these two expectations of random characteristic polynomials. And we study this formula as n tends to infinity. If you look at the unitary group side as n tends to infinity, and you look at its log asymptotics, they behave like an integral against free convolution. Conversely, if you look at the symmetric group side, and you look at its asymptotics, log asymptotics, they behave like the solution to an optimal transport problem. And just combining these ingredients we have on this slide, we obtain a main result, so this is work with Octavio, that if mu and u are any probability measures on the real line with compact support, and z is a real number that's larger than the essential supremum of the supports, then this integral of a log potential against free convolution has to be equal to the solution of an optimal transport problem involving this entropy penalty. So using this expression, you can actually solve this optimal transport problem explicitly. You can describe explicitly the coupling pi that achieves this supremum. And I should emphasize the coupling pi that achieves this supremum depends on your real number z. But you can find this coupling explicitly. And from this formula here, you can evaluate the right-hand side and show that this leads to the characterization of free convolution in terms of R transforms and all of that business. But another thing you can do as an application of this formula is you can plug in any coupling you like of the random variables x and y and obtain an inequality between the left-hand side and the right-hand side of this formula. Namely, if we plug in pi equal to the product measure, in other words, the coupling where x and y are independent random variables, then the relative entropy of this coupling against product measure is 0. And we obtain this inequality relating integrals of logs against of free convolution versus classical convolution. So that's just an example of this entropic optimal transport description of free convolution. Okay, so I want to close by finally discussing how free convolution conjecturally seems to emerge from the statistical physics behavior of these hives, which Harry discussed. So from a kind of geometric perspective, a hive is simply a concave function phi defined on a triangular lattice Tn. So here I have my triangular lattice Tn, and I have a concave function phi defined on the vertices of this lattice. Now, it turns out that this hive, this geometric object, for reasons that still aren't entirely clear to me, this geometric object actually encodes all of the Horn inequalities. It encodes the trace equality and all of the Horn inequalities for AIs, BIs, and CIs being the amount of change the hive has between the boundary vertices. So in Knudsen and Tau's proof of Horn's conjecture, they actually proved it by, to my understanding, using these hive objects. So Knudsen and Tau came up with this kind of alternative formulation of Horn's conjecture, which states that there exists Hermitian matrices A plus B plus C equal to 0, if and only if you can draw a concave function defined on this triangular lattice Tn, where the height changes along the boundary of this function, AI, BI, and CI, match up with the eigenvalues of Hermitian matrices. Sorry, I kind of bungled that sentence. AI, BI, CI are the eigenvalues of Hermitian matrices satisfying A plus B plus C equals 0, if and only if there's a hive with AI, BI, CI as their boundary height changes. So to get a kind of glimpse of how this geometric object encodes all of the Horn inequalities, consider the trace equality, which Harry mentioned. Namely, that if you travel around the boundary of this hive and you look at how much your height changes, it changes by the sum of the AIs plus the sum of the BIs plus the sum of the CIs. But your height when you've traveled around the boundary of the hive is the same as where you started. So your total height change has to be equal to 0. So that's the same as saying that the sum of the AIs plus the sum of the BIs plus the sum of the CIs is 0. So the trace equality somehow emerges from the fact that your height doesn't change as you walk around the boundary of this object. And then you might imagine that somehow the possibility of drawing a concave function with these boundary conditions somehow puts a load of inequalities relating to AIs, BIs, and CIs. And it turns out that these inequalities are precisely the Horn inequalities. Okay, so to relate this object to free probability and to try and get an idea of how free convolution emerges out of the Horn inequalities, I want to introduce a kind of probabilistic version of this theorem that Harry mentioned again, but due to Cockrow and Zuber. They showed that if you choose a random hive in the right way, so you fix boundary height changes AI and BI along two of the boundaries of this shape, and then you choose a random hive in the right way, it turns out that the random height changes you get on the remaining boundary have the same law as the eigenvalues of a sum of random matrices A and B, independent random matrices A and B with eigenvalues AI and BI. Yes, so that's where this star comes in. Yes, so yeah, you choose a hive uniformly at random, and then you bias whatever choice you have by this van der Monde factor. So you choose a hive in proportion to Lebesgue measure on hives multiplied by this van der Monde factor. The short story here is that there's a way of choosing random hives that somehow recovers the distribution of the eigenvalues of a sum of two random matrices. So again, how might a free probabilist look at this problem? Well, we know for a fact that if AIs and BIs, if n tends to infinity, and these AIs approximate some probability measure mu, and the BIs approximate some other probability measure nu, we know that as n tends to infinity, for some reason, these CIs must approximate the free convolution. They must concentrate around the free convolution.
So just to confirm, so
Yep.
if you just prescribe the A's and the B's, and then you happen to know that there is a hive
Yep.
of some kind, that gives you a coupling between the A's and the B's, right? This gives you a coupling between the two measures in some way. Because you've jointly realized the two variables A and B, or it's not the case.
Sorry, I'm not sure I understand.
I'm just saying that so you have your matrices, you have prescribed the eigenvalues of the matrix A and prescribed the eigenvalues of the matrix B.
Yep.
Now let's say you fix the hive with
Yep.
with those boundary parameters. Does that give you a particular realization of the matrix A and the matrix
Yeah,
B, which then when added gives you something?
I don't know, yeah. Yeah, all I know is that the matrices must exist, but I wouldn't know how to construct them out of the hive. But maybe it is known how to construct matrices explicitly. Yeah.
So it is in principle a coupling between A and B,
Yes, yeah.
and therefore a coupling between the two probability measures.
Yes, I guess, yeah. But yeah, so this hive here gives us a kind of problem. It's suggestive that if we choose a random hive in the correct way from the set of hives, where the boundaries on the northwest approximate a probability measure mu, and the height changes on the northeast approximate a certain probability measure nu, then it should be the case that the remaining boundary, the height changes asymptotically, concentrate around this free convolution.
Why do you say this suggests? Isn't this a consequence of it?
Yeah, sorry, it's a consequence. Yeah, it's definitely true. Yeah, yeah, that's a good point. But yeah, so this kind of raises a natural question. Suppose we don't know anything about random matrices, about eigenvalues, about free probability, but we can treat this as a purely purely a question about the statistical physics of random surfaces. Namely, we can define a hive as some sort of surface. We can define a random hive. We can choose a random hive according to some boundary conditions. Can we show that somehow this free convolution operation on two measures is emerging from this statistical physics problem involving random surfaces? And there's been some really exciting recent work by Harry and co-authors, Narayanan Sheffield and Tao, have recently established concentration results. Namely, broadly speaking, it's been shown that the hive does concentrate, tell me if I'm getting this wrong, it does concentrate around a sort of perfect shape. In the GUE case, yeah, okay. Yes, yeah, okay. So we know if the AIs, BIs, and CIs have the same distribution as GUE eigenvalues, then it does concentrate around a perfect shape that minimizes some sort of surface tension integral. But we don't know what that surface tension is. And we don't yet have explicitly free convolution emerging purely from a kind of statistical physics study of these random hives. So it's a really interesting open problem to describe how free convolution emerges from the statistical physics behavior of hives, which describe the eigenvalues of matrix sums. Okay, so in the remaining 5 minutes, I'm just going to race through how we have, how we've had success recently with a kind of parallel problem that's easier. Namely, if you replace free convolution with free compression, which is an operation in free probability describing the asymptotic behavior of eigenvalues of minors of large random matrices, and you replace hive by an object called a Gelfand-Settlin pattern, and you replace sums by minors, we have an understanding of how free probability emerges from the statistical physics behavior of a random surface. So the object, a Gelfand-Settlin pattern, which encodes the eigenvalues of the minors of a matrix, is a bunch of real numbers that look like this. So if you take a deterministic matrix A, and its eigenvalues are lambda 1 through lambda n, and you look at the successive eigenvalues of its successive principal minors, then the eigenvalues of the minors form one of these guys. So here we have k points on the kth row, and these correspond to the eigenvalues of the k by k minors. Now, it turns out, due to Cauchy's interlacing theorem, the eigenvalues of successive minors have to interlace. So these n-1 points have to kind of sit between the n points on the string below. So this is a purely deterministic statement about the eigenvalues of minors of matrices. They form patterns like this. So in analogy to how Cockrow and Zuber showed that a random hive captures the law of the eigenvalues of a sum of random matrices, it turns out that a random Gelfand-Setlin pattern captures the law of the eigenvalues of a minor of random matrices. So there's this result attributed to Baryshnikov from 1999, which says that if you take a random matrix A with these eigenvalues, by random I mean unitarily invariant random matrix, and you look at its random Gelfand-Setlin pattern, then it turns out, in a correct sense, its random minor process is equivalent in distribution to a uniformly chosen Gelfand-Setlin pattern with this fixed bottom row, lambda 1 up to lambda n. In other words, you take a Gelfand-Setlin pattern in proportion to Lebesgue measure on these Gelfand-Setlin patterns. Now, free compression, this operation in free probability, describes the asymptotic behavior of the minors of random matrices, the eigenvalues of minors of random matrices. So we have explicit formulas in the free probability literature for this compression operator, which describes the asymptotic minors of random matrices. But can we obtain these formulas from a statistical physics approach? In other words, let's consider the purely kind of probability statistical physics exercise, where we ignore any relationship with eigenvalues or free probability. If we take a large Gelfand-Setlin pattern at random, where the points on the bottom string are distributed according to some density profile, can we describe the shape of this pattern overall? So Shletenko and Tao recently observed the following, that if you take the quantile function of T compression, so T compression, I'm being a bit informal here, but it's this probability measure that describes the eigenvalues of a Tn by Tn minor of a large random matrix. And if you write phi Tr as the quantile function of T compression evaluated at R, so this is kind of like the rth largest eigenvalue of the T compression, then you can construct a function phi defined on a triangle like this. And what Shletenko and Tao observed is that this function phi appears to satisfy or appears to minimize a certain surface tension integral. So much the same way as a hanging chain will minimize its gravitational energy, or a soap bubble will minimize its surface tension, this free compression operation, when unpacked in the right way, appears to minimize a certain integral. It's the solution to a calculus of variations problem. I'm going to rush instead of overrunning. Shletenko and Tao found that explicitly it minimizes this guy here. And Shletenko and Tao conjectured that this function here emerges out of statistical physics properties of interlacing patterns. And this prediction agrees with non-rigorous work in statistical physics by Sun, work with Neil O'Connell, and also Gordenko. So in recent work, it's shown that these interlacing patterns on a torus are fully integrable, in that you have explicit access to explicit formulas for partition functions and correlation functions in terms of Fredholm determinants. This involves a continuous analog of the Castellin theory approach, which is used to count the number of domino tilings of a chessboard. You can use these formulas to obtain explicit formulas for the volumes of certain bead configurations that are translation invariant, blah, blah, blah. And these formulas have asymptotics that look like this. And these asymptotics of these formulas match the predicted free energy of the bead model, occurring purely from these formal calculations in free probability. You can unpack a Gelfand-Setlin pattern in terms of a surface that looks like this. A random Gelfand-Setlin pattern with a fixed bottom row creates a random surface with a fixed height along the diagonal. The interlacing constraint means that this surface is increasing in both coordinates. So this is just literally just a random surface chosen randomly uniformly from the set of surfaces that are increasing in both coordinates. Okay, in recent work with Yosha, we proved that these surfaces macroscopically converge to a shape that minimizes a surface tension integral. In fact, we prove a sort of large deviation principle for such surfaces. And finally, we show that if you integrate the total surface tension over this surface, if you take the kind of perfect minimizing surface and integrate the amount of surface tension or free energy over the surface, the value of the integral at the minimizer is equal to the free entropy of the probability measure mu. But that was a bit of a rush. So the statistical physics behavior of Gelfand-Setlin patterns recovers free compression and Voiculescu's free entropy. But can we do the same for the hive? So this, to me, it seems like a really interesting open problem. Okay, thank you, everyone, for listening.